Hi everybody. Today we are going to discuss some topics of the paper Nuclear and Particle Physics for 6th semester BSc Physics students of Kerala University. The content we are discussing here are nuclear fission, energy released in fission, Bohr and Wheeler's theory, chain reaction, multiplication factor, critical size, atom bomb, nuclear reactors, breeder reactors, and uses of nuclear reactors. Nuclear fission is the subdivision of a heavy atomic nucleus such as that of uranium or plutonium into two fragments of roughly equal mass. The process is always accompanied by the release of a large amount of energy. In nuclear fission, the nucleus of an atom breaks into two lighter nuclei. The process may take place spontaneously in some cases or may be induced by the excitation of nucleus with a variety of particles such as neutrons, protons, deuterons or alpha particles, or with electromagnetic radiations in the form of gamma rays. In the fission process, a large quantity of energy is released, radioactive products are formed, and several neutrons are emitted. These neutrons can induce fission in a nearby nucleus of fissionable material and release more neutrons that can repeat the sequence, causing a chain reaction in which a large number of nuclei undergo fission and an enormous amount of energy is released. If controlled in a nuclear reactor, such a chain reaction can provide power for society's benefit, such as our Kudamkulam nuclear power plant. If uncontrolled, as in the case of the so-called atomic bomb, it can lead to an explosion of awesome destructive force. Nuclear fission was first achieved by the team led by German chemist Otto Hahn in 1938. Along with his colleague Fritz Strassmann, Hahn found that uranium atoms could be split by bombarding them with neutrons. Then Hahn contacted Lise Meitner, a former colleague and physicist based in Sweden. Lise Meitner, together with her fellow physicist Otto Robert Frisch, showed how fission really worked. In fact, nuclear fission was theoretically explained by Lise Meitner and Otto Robert Frisch. For his discovery of nuclear fission, Otto Hahn was awarded the Nobel Prize in 1944. Now coming to the nuclear fission process, we can write the schematic equation for nuclear fission process like this. Uranium-92-235 plus neutron gives uranium-92-236 with a star, which gives X plus Y plus neutrons. Here uranium-92-236 star is a highly unstable isotope and X and Y are fission fragments. There are various combinations of fragments possible as given here. X and Y can be barium and krypton, or xenon and strontium, and Q is the energy released in the reaction. This is the pictorial representation of this equation. That is, when uranium-92-235 is bombarded by a slow moving neutron, the nucleus becomes unstable uranium-92-236 and splits into barium 56-141 and krypton 36-92, releasing 3 neutrons and energy Q. Next is about the energy released in fission. We know that the nuclei consist of nucleons, that is neutrons and protons, and the total number of which is equal to the mass number of the nucleus. The actual mass of a nucleus is always less than the sum of the masses of the free neutrons and protons that constitute it. The difference is the mass equivalent of the energy of formation of the nucleus from its constituents. The conversion of mass to energy follows Einstein's equation E is equal to mc square. Here E is the energy equivalent of a mass m and c is the velocity of light. This difference is known as the mass defect, and it is a measure of the total binding energy of the nucleus. And this binding energy is released during the formation of a nucleus from its constituent nucleons, and it would have to be supplied to the nucleus to decompose it into its individual nuclear components. We can calculate the binding energy using this equation. Here Z is the number of protons, Mb is the mass of the proton, N is the number of neutrons, N is the mass of neutrons, C is the velocity of light, Mn is the nuclear mass. The binding energy per nucleon is equal to total binding energy of a nucleus divided by number of nucleons it consists. This figure shows the average binding energy per nucleon as a function of the nuclear mass number. Here we can see that the largest binding energy, that is highest stability, occurs near mass number 56, which is the mass number of the element iron. Thus we can say that any nucleus heavier than mass number 56 would have become a more stable system by breaking into lighter nuclei of higher binding energy, and the difference is in this binding energy is released in the process. Now let us calculate the energy liberated per fission of a compound nucleus of uranium-92-236. From this binding energy curve, for a heavy nucleus, for example mass number 236, the average binding energy per nucleon is approximately 7.6 MeV. For a nucleus with a medium weight, it is about 8.5 MeV, and this difference is 0.9 MeV. Hence, we can say that the average binding energy per particle is about 0.9 MeV more in fission products than in a compound nucleus uranium-236. Thus, this excess of 0.9 MeV per nucleon must be liberated in this fission process. So, we can calculate the total energy liberated per fission of uranium-92-236 as shown here. 8.5 minus 7.6, which is equal to 0.9 MeV, into number of nucleons, which is 236, which approximately gives 212 MeV of energy. There is another method to calculate the total energy released by considering only the fission products. For example, consider the reaction neutron plus uranium-92-235 gives molybdenum 42-98 plus xenon 54-136 plus 2 neutrons. Here the total mass of the nuclei before fission, which is the sum of the mass of reactants, is 236.0526 AMU, and the total mass of the nuclei after fission is 235.8306 AMU, and the difference is 0.222 AMU. And we have 1 AMU is equal to 931.3 MeV. So here we have 0.222 AMU. So the energy released is equal to 0.222 into 931.3, which is equal to 206.7 MeV, which is the second method to calculate the energy released for a single fission. From both methods, we got nearly 200 MeV of energy as result. Now, can you calculate the energy released by 1 kilogram of uranium? For this, we have to calculate the number of atoms in 1 kilogram of uranium. We know that the number of atoms in 1 gram of any substance is Avogadro number divided by its atomic mass. That is 6.023 into 10 raised to 23 divided by atomic mass of that substance. For 1 kilogram, we have to multiply this with 1000, that is 10 raised to 3. So the number of atoms in 1 kilogram of uranium is equal to 6.023 into 10 raised to 26 divided by 235. We have already calculated the energy released in one fission of uranium-235 as 200 MeV. So the energy produced by 1 kilogram of uranium during fission is 6.023 into 10 raised to 26 divided by 235 into 200, and we will get the result in MeV. We can convert this into joules because 1 MeV is equal to 1.6 into 10 raised to minus 13 joules, and we can convert this into kilowatt hour. 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. So the result is 2.26 into 10 raised to 7 kilowatt hour. Thus we have noticed that the energy released by fission of 1 kilogram of uranium-235 is 2.26 into 10 raised to 7 kilowatt hour, which is a large quantity, and due to this reason nuclear energy is used for the generation of electricity. Next is about Bohr and Wheeler's theory of nuclear fission. Niels Bohr and John A. Wheeler explained the nuclear fission process with the help of liquid drop model. You know that a liquid drop has a spherical shape due to surface tension. On applying external force, the sphere changes into ellipsoid, which may change into a dumbbell shape when the force is larger. This may break at a narrow end into two portions. In the same way, when a heavier nucleus absorbs a neutron, a compound nucleus is formed and is left in an excited state. The extra energy may set up a series of rapid oscillations in the spherical compound nucleus. As a result of these oscillations, the shape of the compound nucleus may change at times from spherical to ellipsoidal. If the extra energy is too large, the compound nucleus undergoes distortion from ellipsoidal to dumbbell shape. Each portion of the dumbbell has a positive charge and one repels each other. This results in fission and formation of fission fragments. This is the explanation of nuclear fission by liquid drop model. Next is about chain reaction. It is a self-propagating process in which number of neutrons goes on multiplying rapidly almost in geometrical progression during fission till whole of the fissile material is disintegrated. For example, suppose a single neutron causing fission in a uranium nucleus produces 3 neutrons. These 3 neutrons may cause fission in 3 uranium nuclei producing 9 neutrons. These 9 neutrons may cause fission in 9 uranium nuclei producing 27 neutrons, and so on. The number of neutrons produced in n such generation is 3 raised to n. The ratio of secondary neutrons produced to the original neutrons is called the multiplication factor. It is defined as K is equal to number of neutrons in any one generation divided by number of neutrons in the preceding generation. The fission chain reaction will be critical or steady when K is equal to 1, and it will be building up or supercritical when K is greater than 1, and it will be dying down or subcritical when K is less than 1. Next is about the critical size for maintenance of a chain reaction. For a chain reaction to occur, the size of the fissionable material must be above the size called the critical size. The escape of neutrons takes place from the surface of the reacting body, and fission, that is the production of neutrons, occur throughout its volume. Thus, the greater the size of the system, the lesser is the probability of the escape of neutrons. So, the critical size of a system containing fissile material is defined as the minimum size for which the number of neutrons produced in the fission process just balance those lost by leakage and non-fission capture. The mass of the fissionable material at this size is called the critical mass. A chain reaction is not possible if the size is less than the critical size. The idea of critical mass we have discussed here is the heart of the gun assembly atomic bomb shown here. Two subcritical masses of uranium are at either end of the gun barrel. One is shaped like a hollow bullet, while the other is a cylindrical target that just fits within the bullet. Conventional explosives shoot the bullet down the gun barrel where it mates with the target. The two subcritical masses were brought together rapidly, form a supercritical mass, resulting in a chain reaction and an atomic explosion. The atom bomb is due to an uncontrolled chain reaction, but in a nuclear reactor, the chain reaction is brought about under controlled conditions. So we can say that a nuclear reactor is a device to initiate and control a sustained nuclear chain reaction. A nuclear reactor consists of 5 main elements. They are the fissionable materials called fuel, moderator, neutron reflector, cooling system, and safety and control systems. The first component is the fissionable material called fuel. The commonly used fuels are the uranium isotopes uranium-233, uranium-238, thorium isotope thorium-232, the plutonium isotopes plutonium-239, 240 and 241. The second element is the moderator. Its function is to slow down the neutrons from high velocities and hence high energy level which they have on being released from fission process, so that probability of neutron to hit the fuel rod increases. The main moderators use the heavy water, that is D2O, graphite and beryllium. The third component is neutron reflector. It is placed around the core to reflect back some of the neutrons that leak out from the core surface. The next element is cooling system. A coolant is used to remove intense heat produced in the reactor. That heat can be transferred to water in a separate vessel which is converted into steam and runs the turbine. The main coolant used are water, carbon dioxide and helium. The next component is control and safety system. The control rods are usually made up of cadmium or boron. It slows down the rate of reaction to a controllable limit. Otherwise, the chain reaction blows up like a nuclear bomb. Raising and lowering the control rods allow operators to control the rate of the nuclear reaction. This figure shows a power reactor. The control rods regulates the temperature to a predetermined value. If it is desired to bring down the temperature, the control rods are pushed down further as to absorb more neutrons. If the temperature has to be raised, the control rods are pulled up a little. Here a fluid is circulated through the shielded reactor and heat exchanger. While a hot fluid is flowing through the heat exchanger, it converts water into steam. This steam produced runs conventional turbines to produce electricity. There is a condenser which converts the steam to water. Cold water from a river, lake or ocean is used for this purpose. Next is breeder reactor. Conventional nuclear reactors use uranium-235 as their fuel. However, uranium-235 makes up less than 1% of naturally occurring uranium. Most uranium occurs as the isotope uranium-238. The only problem is that uranium-238 can be used in conventional nuclear reactors. It doesn't undergo fission like uranium-235. The breeder reactor was developed to use uranium-238. Here is how it works. The uranium-235 core is surrounded by a layer of uranium-238. As uranium-235 undergoes fission, it releases neutrons. These neutrons converts uranium-238 to plutonium-239. That is, a reactor breeds fuel plutonium-239 as it operates. Thus, a breeder reactor is a nuclear reactor that breeds nuclear fuel. The last topic is the uses of nuclear reactors. Applications of nuclear energy and radiation have played a significant role in the field of electricity production, scientific research, medicine and health. Radioisotopes are made in nuclear reactors. Some reactor radioisotopes and its applications are given here. Nuclear reactors produce a number of radioactive materials needed for research purposes. They provide a number of neutrons, and using these neutrons, several useful radioisotopes can be artificially produced, and several nuclear reactions can be studied. We can study the effect of neutrons on biological tissues. Reactors can also be used to study the radiation damage. That's all. Thank you.